Well, it's my pleasure today to introduce Eric Baum, who is still listing his affiliation as NAC here, although on his homepage he notes that in a week he'll no longer be there. He is trying the Wall Street route, at least briefly. Am I allowed to say this? Is this good to say?
No.
Yeah, that's good stuff. It's a world that he knows well about marriage.
Are you going to read this now? No.
But he's not leaving the field, so no fear. Eric, so a lot of what we do in statistical speech and language processing is search of very large spaces. Sometimes there are large, like the space of all parses or the space of all alignments and translations, and often what we're concerned with doing is either starting at a current solution and improving it, or piecing together a number of sub-solutions, for example, by dynamic programming. And we're always looking for better ways in which to do this kind of thing. Eric's work has a very different perspective on these problems. It has elements of hill climbing, and it has elements of piecing together solutions of a large problem, but actually in much larger search spaces. The things that he's putting together are not pieces of a parse, but pieces of code, which can collaborate to find a solution. So I hope while we're listening to his talk, we can also think about how we might apply these problems for extremely large search spaces to the more modest but still large search spaces that we encounter on a daily basis. Eric did, like a number of people in this field, did his PhD originally in physics at Princeton, and he was at a number of places since then, including JPL, Princeton, and Berkeley. Is that right? Yeah. Before changing fields and ending up at NAC. So, without further ado, thanks very much for coming.
So this will report work from a number of papers, which all but the first couple were joined with Igor Draganovich, and which the web crawling application is joined also with Eric Cruz and John Hainsworth. Before I get into the body of the talk, let me plug my book, which is coming out next fall from MIT Press. It's called What is Thought? This is chapter 10 of a 15-chapter book. This talk you'll see is about how you can, how an evolutionary program can exploit the fact that there's a very compact description of problem domains and learn to essentially understand them in some sense. And the book is more generally about how mind arose from such a process and what you can say based on that, and sort of a soup to nuts discussion of all various issues that arise. All right, so I've been working on reinforcement learning for a while. I set out in reinforcement learning. One has some world that one interacts with. It's the framework, and you can sense that world, and you can take actions on the world. And when the world gets into certain states, it makes a payoff. And your desire is to learn a strategy of interacting in the world that maximizes your payoff over time. And I've been interested since the start of this, working for some framework that might reach or at least explain how human-level computational abilities might possibly arise. Now, the standard, which sort of constrains the approaches that might be considered. The standard approach to reinforcement learning, especially back when I started, people are looking at other stuff now, is called value iteration. And you assume that the world is described by a state space graph. So in such a graph, there's a circle. I've drawn a circle here for each state the world might be in, and there's an arrow transiting from one state to another if there's any action that takes you from this state to that state. And some of these states are marked with reward. There might be others marked with reward. And the learning approach is you wander around and try and build up a graph in your memory, what the graph is and what you can transit from what to what. And you build by dynamic programming an evaluation function at each state. So if you've got paid 10 there, we might assign this state 10, and then we back that up by dynamic programming and say, well, if we get to this state, we can reach there. So this ought to be valued almost 10 too, maybe this is valued 9. And then we back that up, and if we get to this state, we can reach there, so this state maybe should be valued 8. We back things up along this state, so we get an assignment of an evaluation, a number for each state in the graph. And once you've got that, there's an optimal strategy. It's easy. Wherever you are, you look ahead at all the states you can go to, and you say, what's the valuation of that state? And whichever one's the highest, you take that action, and that's going to give you the optimal strategy. This is there's more detail I could give, but yeah.
But that's only if you can build the whole graph, because if you still have exploration to do, you don't know.
Yeah, so, right, this is the standard picture, and this is, I'm putting this up as a straw man to critique. But if you can build the whole graph, then this gets you the optimal. But it's useless for any real problem, because any real problem, the state space graph is going to be absolutely enormous, if not infinite. So I contend that this is sort of the wrong picture to do. Now, of course, when people actually come to solve real problems, which they do to some extent using a picture like this, they can't assign a number to each state in the world. So what you do is you train a function approximator, like a neural net, that does generalize, tries to generalize and predict the value of states that you haven't ever been in before. And then you look ahead and see which action leads you to something that your neural net predicts as the highest valuation, and you follow that. And that works pretty well. It solves some interesting problems. Like, for example, the best one is it did a pretty good job on backend. But I contend that this approach is still based on the underlying principle that there's a state space graph. Conceptually, you're thinking that there's a state space graph, and you're learning about the state space graph. And what we know from computational learning theory, and especially if you want to get to anything that's going to explain human-level computational abilities, you're really going to have to exploit the fact that the world has a very compact description. And you don't want to work with the state space, which is absolutely huge. There's some compact description that tells you everything you want to know and blows up into the state space graph, but you want to work with some program on the actual compact description. And you're never going to get there, I contend, if you start with anything that thinks that you're really working on the state space graph. And a consequence of this, just for another problem, which makes clear that this is a real problem, is that when you start training a neural net, you're sort of assuming that there's an evaluator you're going to produce that shows progress after a single action. And for real problems, that's not generally going to be the case. Consider Rubik's Cube, which is a problem that I'll talk about later, so maybe you're familiar with that. In Rubik's Cube, humans don't learn how to solve it by learning to recognize progress after a single action. They learn some sequence of actions that goes far enough in the right direction that they can recognize progress. And that's sort of the minimum you're going to have to do. For real problems, it's not clear that trying to find an evaluator that will show progress after a single action is even a step in the right direction. So let me give you another problem domain, which is a concrete and simple problem that nonetheless has a long history that is a good thing to use to describe what our approaches are, and I'll talk about other problems shortly, which is the block scroll domain. In this problem that I'm going to address, what you see is a series of instances. Each instance consists of 4 stacks of colored blocks. And you control a robot arm, the learner controls a robot arm, that if it's empty, can pick up the top block on any of the rightmost 3 stacks, and if it's holding a block, can put it down on any of the rightmost 3 stacks. And it's supposed to learn somehow, just from getting reinforcement, how to pile these up. If it piles them up here, so that the stacks are identical, then it says done, it gets a reward. We go on to the next instance. And if it says done prematurely or it times out, then it doesn't get a reward, and we go on to the next instance. And we like to learn to solve these reinforcement learning problems. Now, this is an example of the kind of problem I'm talking about. It's got a compact description, which I just gave you in a paragraph of text. Yet, any given instance has an exponential number of states, and since I can give you arbitrarily large distances, the number of states is actually unbounded. So we've got a good example of the kind of problem that I'm talking about. And I'd like to be able to train my learner with instances of increasing size. I have to give it small instances at first, because at first it's going to be pretty random, and it doesn't learn anything until it gets rewards. So I'll give it small instances, and it'll solve those. And as it learns to solve small instances, I'll give it bigger instances. And I'd like it to learn to extract some program that understands that there's a compact structure underlying these problems and knows how to solve them. I tried as a straw man here, training up sort of standard TV learning, training a neural net, and I gave it a very useful feature, num-correct, which we'll meet again later, a hand-coded feature that tells it how many blocks it has correct on the one stack. That's a pretty useful feature. And I didn't require it to say done. If I didn't give it this, or I did require that, it did much worse. And whenever it got it done, I told it was done. And then it got up to solving about 8-block problems. So that's a sort of standard, what you might expect if you just train a TD learner here. This problem has a history going back in the planning literature. People have been trying to solve blocks world problems as planning problems of various natures for 30 years probably. And if you don't know anything about the domain structure, you're essentially just doing an exhaustive search, and you run into this exponential hurdle. You don't get very far. So that off-the-shelf AI planners solve about 5-block problems, and then they run out of steam. And maybe 4 or 5 years ago Baum and First came up with the notion of compiling planners, which tries to extract constraints from the world to some degree, and cuts the search space, but it's still exponential. I don't think that their compiled planners actually would solve these problems at all, because of having this very constrained set of places where I could put blocks would make it, I'm not sure how that would fit in with their thing. As far as I know, nobody's tried it, which is not a good sign. But people have tried using plan compilation type of algorithms on blocks world problems where you've got a flat table that you can put all the blocks start on, and you're just trying to stack them up into an order. And then it gets up to about 100-block problems and runs out of steam. Its exponential growth catches up with it, and it's really doing exhaustive search of a more constrained space. So to get to 100 from 80 sort of multiplies the amount of time it took by some large factor. But it's out of steam at that time, yeah?
Sorry, in the flat problem, initially every block is in its own tile that you're starting with?
Every block's its own pile, and you just got to figure out how to stack them all and get them in the right order.
Okay, so that problem is trivial for a human. So.
Yeah, this problem's pretty trivial for a human. It's not that hard.
Right, unless you have some resource constraint.
Right, yeah. But so for that problem, they can get up to 100-block problems.
Excuse me, the target is always to imitate some...
The target here is to imitate the zero stack, yeah. Each problem instance, you're going to get a
problem you talked about with him, mainly that it's a flat start, it's still...
Yes,
yeah.
You're imitating. Yeah, actually, maybe in these problems, they might have multiple stacks. You total 100 blocks with some set of target stacks.
And the machine knows the colors and all that?
Machine knows the colors and all that, yeah. But the algorithm that they're using is off-the-shelf planning algorithm of one type or another, either compiled or not uncompiled. And so it's essentially doing, you know what the problem is, but it doesn't really know what the problem is. It's doing this exhaustive search, which is my point. If you don't really understand the domain, you got problems. Another point here, by the way, which I should make, is that this is, again, it's an instance where it's really not clear that there's anything you're going to learn which tells you when you've made progress after a single instance. Right? Even if I give you num-correct, even if I give this guy num-correct so that it knows how much progress it's made, making the next progress might require taking, the next block it needs might be pretty deep down in some stack, and it's got to realize that when it takes the top block off that and puts it on something else, even though it's putting it on other blocks that it's going to need later, it's making progress. That's not so obvious how you learn that. It's not so obvious how you learn this num-correct. It's not clear that setting out to find a evaluator that shows you progress after one step is an improvement in trying setting out to try and learn the problem.
Is the point that it actually cannot examine the colors of the zero stack?
The planner?
Yes.
I mean, no. The point is that the algorithm.
if you could examine that the bottom is red, so it just looks for the first red thing, you know.
Your question is why are generic algorithms so stupid? It seems hard to believe, but they are.
But they are, yeah. Okay. I'll give you a citation. This was a feat, right? I put this here because it was a great feat that they got up to 100 blocks on the. All right. So if I'm dissing the standard methods, what am I going to try and do in what's the alternative? And in the reinforcement learning community, there was, and it's now being studied a little more, an alternative approach, policy iteration, which is never mind trying to learn a value function, we'll try and learn a policy, we'll try and learn a strategy. And they talk, in the reinforcement learning community, they talk about trying to learn parameters of policy. Bigger community is a little bit more ambitious and sort of after the same goal, evolutionary programming, we're just going to, if you're going to exploit this kind of compact structure, you're going to have to take for granted that you're going to have to produce a program. The program's going to have to learn what the structure is and how to exploit it. So we're going to have to evolve a program that senses the world, it computes what to do, it decides what to sense next, decides what actions to take and what more computations. It's a program. And you know, one advantage of this, which motivates my work in the book and how it connects to this, is that this is where we came from. We are an evolved program such as that. At least I'm arguing in 15 chapters. That has learned to exploit the structure of the world. So, in some sense, at least it's possible in principle. But if you want to do it on your computer and do anything useful, you've got some problems. It's not so easy to do this, which is why the sort of reinforcement learning community sort of dissed evolutionary programming for a long time. The main problems are, well, first of all, I said that we had a big space in terms of the number of states, but in some sense the number of behaviors, the number of programs is even bigger. How are we going to search through this space and find programs that work? And also, as we're doing this, there's a very rough fitness landscape typically. When I change one line of code in my program, it might do something totally different, so it's not so easy to just sort of evolve it and get it to do the right thing. So, in particular, if you take off-the-shelf the main evolutionary programming algorithm is genetic programming. If I try that on Block's World, and I think I told it done also, and gave it non-correct, and it solves about 4 block instances. Doesn't even do as good as this other thing. And at that point, it's done. You can look at it and you see that it's thrown out half the instructions it needs, and there's no way, it's in a local optima, and it's not going any further. And run this numerous times, and it's stuck. And that's true for genetic programming on all the different problems. I've tried them on every problem I'm going to tell you about, except for the web crawling problem, and it's pretty hopeless. And I've tried using exactly the same instruction sets that I'll talk about, and it really doesn't get there. Okay, so what am I going to do to improve on this? Here's the notion. I'm going to say, since I'm trying to find a way to search this huge space of programs, I'm going to adopt an inductive bias, essentially, that my program is going to be composed of a bunch of interactive modules. I'm going to try and factor the program. I'm going to try and divide and conquer it so that I don't have to solve the whole thing at once. I'm going to try and get so I can solve a bunch of pieces of it. And the way I'm going to do that is I'm going to try and assign them credit. So I've got a bunch of different modules, and I'm going to have a framework such that these modules hopefully get credit for their contribution to the performance of the whole program. And if I can do that, then the individual modules just reinforcement learn happily. They don't even have to know what they're reinforcement learning. They're just moving around trying to figure out how to improve their performance, how to improve their reward. And everybody does that, and hopefully they divide up the problem and factor it, and we make a lot more progress. It's easier to solve than doing it all at once. That's the big picture goal. So how do I do that? Well, I took inspiration for this from the economy, which essentially does exactly that. I was reading one day a story of a pencil, which is what actually stimulated me on this. The question is, when you go into a store, a stationery store, and you buy a pencil, how did that pencil get there? And the answer is that people, literally thousands of people contributed to that pencil. And they don't know each other, and they have no common purpose, and they don't even speak the same language. They're literally rapeseed farmers in Indonesia who are growing rapeseed that gets processed into oil that goes into the graphite. And then there are smelters who deal with the little brass ring, and these guys don't have any common purpose. They're each just going after earning money themselves. And Adam Smith's invisible hand somehow coordinates all their actions. So what I'm going to do is to try and do the same thing here. I'm going to run an artificial economy. My agents in my economy are going to be computer programs with some money, and they're going to pay each other money, and they're going to take actions, and money's going to flow into the system when they do the right thing, and it's going to get routed around by the economy. And when these guys go broke, that'll be because they're not doing the right thing, and I'll remove them. And then I'll insert new ones typically by just mutating rich ones that I've got there. And the system will thus evolve, and hopefully it'll solve the problem. So I drew this picture before of the state space graph. Now I've got another graph that looks sort of superficially similar, except that now, instead of being states, these guys are agents. And money's going to flow into the system from the world when they solve it. It's going to get passed around by some kind of dynamic programming procedure on agent space. And so I'm hoping to pass money to the guys as they contribute to collaborating and get them to evolve to do the right thing. Now, I claim intuitively that this works in my system, and I also give some a lot of empirical evidence that this is true, that this works in my system, and it works in the real world, in the economy, for if and only if two principles are imposed on the system, and because you get dynamic programming when these principles are imposed. The invisible hand is basically dynamic programming, I claim. So the first thing you have to have is you have to have conservation of money. When agent A, there's going to be money flowing into the system from the world when they solve stuff, and there's going to be money flowing out at the beginning of the instance. But basically, when one agent pays, the other agent has to get it without any leakage or without any money magically appearing. And the reason for that is if you want to have a long sequence of agents and push a reward back down a sequence so that the early guys who take an action that later sets up another guy, sets up another guy, if they're going to get properly compensated, money better not be leaking, or else maybe you go back 3 links, but you're not going to go back any further than that. So you can't have money leaking out, and also you certainly can't have money being created, because you'll go around in loops creating money, and the system will happily learn how to do that without solving the problems of the world. And every time you get a bug in your program so that it learns how to create money, it immediately gets rich and it's not doing anything. It learns that, exploit that immediately, because solving the problems of the world is hard, but exploiting the bugs in the program is easy. So you need conservation of money. The other thing you need is everything in the system. You need to enforce property rights, and everything in the system has to be owned. And why is that? Well, let's assume that we have a collection of agents that are rational for the moment. In the strong economic sense, they always do the right thing for earning money. And a new agent is trying to come into the system. Now, I claim that if everything is owned in the system and we have conservation of money, this new agent is going to be able to enter profitably if and only if it actually improves the performance of the system. And why is that? Well, if it doesn't improve the performance of the system, it can't get any money from anybody else because they own it and they won't give it to them. And it can't get any money from anything anywhere because everything's owned, so it has nowhere to get money. But if it improves the performance of the system, then more money flows into the system, and there's money to lie around, and since they're rational, they're all happy to give him some of it, and they get a little bit more, and everybody's happy. So if the agents are rational, and these two things are true, then it's a theorem of Coase that a new agent can enter if and only if it improves the performance of the system. Now, in my system, the agents are initially about as far from rational as they could get. In fact, they're literally random computer code. But the guys who are less rational lose their money, they give it away, and they go away. And so gradually, the guys that are more rational survive a little longer, and you hope to bootstrap to where the programs are relatively rational, and then new guys can pretty much enter only if they're improving the performance of the system, and you can evolve hopefully to solve problems. That's the motivation. All right, I could talk a long time about this, but I don't want to spend too much time on it. If you look at the economy and the ecosystem in these terms and other structures, you can say a lot of interesting things. So Miller and Trexler back a ways compared the evolution of the ecosystem, where none of this is enforced, to the evolution of the economy. In our artificial economy, we're totally enforcing conservation of property rights because it's my program and I do what I want. In the real world, they get largely enforced. And where they break down, you have troubles. So you have air pollution, arguably, because the air is held in common, so everybody can dump into it, and nobody bears the cost. That's called the tragedy of the commons. And that kind of you have traffic congestion because everybody dumps on everybody else by imposing congestion on them. And that happens all the time. And in ecology, it happens like crazy. Because if A eats B, B loses more than A gains, and nobody even has property rights in their body. So what you get is all of evolutionary effort going into arms races and red queen races, they're called, where the plants who don't want to be eaten develop toxins, and the animals who want to eat them develop complicated livers to digest those toxins. And a lot of effort is going into evolving these things. Just running in circles basically, not getting anywhere. You also get positive feedback loops in other ways. If you don't have conservation of money, you get positive feedback loops. So if the female peacocks decide they like lots of eyes on the male's tails, then it's sexier to like eyes. It's sexier to have a big tail with lots of eyes, so you're fitter. And it's also sexier to like them, because then your sons are fitter. So it's a positive feedback loop, and it can run out of control. If you have conservation of money, that can't happen. So in the ecology, in the ecosystem, Miller and Drexler claim, you get all this complexity and all this stuff going around in circles. In the economy, they claim you get much simpler evolution, where everything's much more structural. You get sort of 3 big corporations, and anyway, there's all kinds of interesting stuff you could say that's kind of off topic. But you do see this similar phenomenon in multi-agent programs. In any kind of evolutionary multi-agent program, you see the same thing. In particular, Lenat's heuristic is a famous one, some of you might know. He had heuristics that were doing stuff, and he had meta-heuristics assigning interestingness to the heuristics. Interestingness was not a conserved quantity, so you had positive feedback loops where the meta-heuristics assigned infinite interestingness to themselves. You had to keep on going in by hand and trying to remove that. Holland's classifiers, which are an early economic model that greatly stimulated my thinking. I don't want to diss them too much, they definitely were an inspiration to me. But he's got multiple agents active at any given time, and when money comes into the system, they divide it, which is a recipe for the tragedy of commons. If anybody thinks money's going to come into the system, they want to be active at that time, even if what they're going to do is going to hurt the system. And for other reasons, he was unable. When Holland's classifiers were first published, everybody had this notion that you can have these long chains, and it never happened. There's still a classifier community 20 years later, but they've given up long since in having chains, and they're just trying for one at a time and doing interesting things there. So I better go on. All right, so that's sort of intuition, since I can't prove anything's going to happen here, but I've tested this through a number of tests. I've tested this for sort of two, actually sort of three, because the web crawling is a third thing. Languages, S expressions, and post-production, and you'll see how that changes how the agents work. I've tested it on three sort of toy domains: blocks world, Rubik's Cube, and rush hour, and now one real world problem, focused web crawling. So it's a total of 6 tests, because I haven't done all these possibilities. And in every case, I've achieved considerable chaining, stable solutions, much better than alternative autonomous methods on any of these games. I mean, really much better. And on the web crawling, it does, as you'll see, pretty good. I don't have a state-of-the-art crawler that's in the public domain that I know how to compare to, but it certainly looks like it's doing pretty well. It's doing about as well as you could hope for, I think, and it's doing sort of better than a standard Bayesian benchmark that people compare to, as you'll see. For blocks world, we get chaining thousands deep for S expressions and infinitely deep for post, whereas previous methods really couldn't get any chaining at all. And in each of these cases, if we break the conservation of money or we break property rights, you get nowhere. So it really looks like these principles are what's underlying progress here. So with that, here's the outline for the rest of the talk. I'll give you the explicit algorithm by which we're running. I'll talk about the post-prediction systems and give empirical results for blocks world and Rubik's Cube. I'll talk about S expressions and give empirical results for blocks world, Rubik's Cube, and a commercially sold game called Rush Hour. Then I'll talk about web crawling, and then I'll conclude. So here's what I do to actually institute this. I initiate my system with a bunch of agents that are random code. So now I hold a series of auctions when I'm actually proceeding.
What's a random code? I mean, go to step 3, do.
I'll show you. You see, when I'll get to particulars of languages. But basically, yeah, I have S expressions. I generate random S expressions by starting. You know what an S expression is? Yes, I start at the root, and I choose a random instruction, and if it's got arguments, I choose random instructions, and I adopt a probability distribution such that it concludes after a while, like having some probability of choosing a terminal at each step, and generate random code over a set of instructions. I'll tell you exactly. So I start with random code over whatever language that I'm using, and I'll tell you about that. Then I hold a series of auctions. In each auction, I look at all my agents. I run their program. If they want to take actions on the world, I simulate it. They're not yet allowed to actually touch the world, but I am simulating it, so I'm giving them sort of access to thinking about the world. For the S expressions. For the post-production, that's not necessary. When I run their program, it might take actions on the world. It returns a number, because that's the way it's constructed. And that number is its bid. Actually, the mid of that number and how much money that agent has is its bid. So it makes the agents make bids. The high bidding agent wins the auction and buys the world.
And gives up the money.
Gives up pays the previous owner of the world. He buys the world from whoever owned it, which presumably was whichever agent bought it in the last auction. Then we take whatever actions his program wanted to take on the world, we actually take on the world, because he owns the world, he can take actions on it now. If the world makes a reward, he collects it, because he owns the world, and then he sells the world to the next agent. We go on. So because he owns the world, so first of all, note that I've achieved my goal here of having the whole world owned. Everything's owned, because I sold it to one guy. It's kind of the most simple way to do that. At the very end, I'll tell you about a more complicated model where you've got multi-commodities for the web crawling. But basically, the simplest thing, and which works pretty well here, is to have one guy buy the world. And because he owns it, he's motivated to maximize its value. What do I mean by that? What I mean by that is the guy who's going to win this auction is going to be the guy who can take the world to a high value state and sell it because he can pay more than everybody else. The guy who can take it to the highest value state can pay more for it. And also he better bid pretty accurately. You know, better estimate how valuable it is, because otherwise some other guy who's a mutation of him that is basically identical to him but just bids a little more will come in and push the bid up. So the guy who wins is the guy who takes the world to the highest value state, pushes it closer to the solution, and bids accurately. Yeah.
It seems like it's not necessarily that he bids it, that he pushes it to a higher state, but just that he pushes it to a state where someone else wants to buy it.
Yeah. If there's some other idiot who's willing to pay him, that's where the rationality comes in. If some other idiot who's willing to take the world off his hands for a lot of money, but that's not stable, right? Because other guy's going to go broke.
But it might not necessarily be that it's actually that they're an idiot. It might be that he's put it in such a configuration that they have the solution. So it seems like...
Oh, yeah. But if he puts it in a state such that they have the solution, then you know then they can get reward from the world. So that's exactly essentially what it means for the state world. What it means for the world to be more valuable is that somebody values it more. But the only way somebody can stably value it more is that they're going to get paid by the world, right? So essentially that's what it means. It pushes it closer to the solution given the context of the other programs and what they're willing to pay. Now, in some runs, so this is evolutionary computing. So you can get guys evolving, you know, huge collections of meaningless stuff that they're doing that isn't really doing anything. To try and keep that down, and also you got to do something to remove agents that aren't doing anything. They're just sitting there and they're not even active. So you have to take some money out of them a little bit to keep them alive. Try very gently to tax them proportional to instruction, to charge them rent for the computing time, because that's my scarce resource. Very difficult to promote evolution of efficient algorithms. Some runs we do this, and some runs we do it less. Very low, because this is essentially pulling money out of the system and sort of views it as breakthrough conservation of money and splat. So this has to be, I haven't found a good way of doing this. This is just a little bit. And then we introduce mutated versions of the successful agents into the population, and it starts evolving, and off we go. All right, so now I'm going to talk about the post-production system. The creation differs just slightly from system to system. But in the post-production system, the agents each have a set of rules. I'll talk about it on the next slide. Usually one rule, but maybe a few rules. So we've got a list of rules in the system and a list of agents. The rules are created at random or as mutations of existing rules. I'll show you what rules look like. And the rules are on the list as long as some agent uses them. And then the agents are created as a mutation of existing wealthy agent, either by mutating a rule or taking a new rule from the list, killing a rule, replacing a rule, shuffling the order of the rules. And the new agent, how does he get a bid? And this is, I'll talk about several models where agents get their bids, but in this model, the agent just bids, we call the bid X model. He just bids the first time that he actually wants to bid, that he actually matches the world and he says, I want to bid now. We have him bid 0.01, minimum amount, more than a competitor when he first applies. So he wins the auction, and we try out this new agent. Good thing to try him out, because otherwise he's just wasting our time. And if he doesn't work and he loses money, we take, he's out of there. But if he works, then good. And the agents exist as long as they're at least as wealthy as when they first came in. Otherwise, we take their money back and give it to their parent and remove that agent as soon as they get poorer than that. And so this pushes the bids up until they're rational. You might have had until they get us up to good estimation. For the web crawling, you want to push things faster because page fetches are expensive. So you'll see we did something else. But this works fine here. Okay, post-production systems. If you don't understand this, it'll become clearer on the next slide when I give examples. Post proved in 1943 that you have this Turing universal model of computation where you've got a string of symbols that's an axiom, and then you've got some productions which have variables that can match a string of symbols and other strings. And whenever one of the productions matches, you go through them in order. And if a production matches, you make a substitution to change the axiom, binding this to whatever it took to match it. And so then we get a new axiom, and then we compute in that way, changing what's posted. And this is a model computation which we're going to use here. So I'm going to present to my system as you get a better idea when I show you the next page. I'm going to present to my system the world as an axiom, which I write as A. We're talking about it for block scroll for the moment. A open paren, B closed paren, open paren, C closed paren, etc. Where A is one color, red or empty, and B is a string of colors, red, blue, white, representing the zero stack, and then C is a string of colors representing the one stack. D is a string of colors representing the two stack. So this codes what the state of the world is. That we present that to the thing. The productions of these agents look like this, where we put in the parentheses, and the S's are strings. over y's, which match a single variable, and match a single color, and xi's, which match a string of colors. And the right-hand action that this agent takes is to grab some string over grab 1, grab 2, grab from stack 3, drop on stack 1, drop on stack 2, drop on stack 3, or stay done. And if this guy matches, then the agent bids. If his bid is high, then we take his action, and that's the way this proceeds. A note here that I have given it where the brackets are. We tried at first to just let it learn everything. In principle, it could learn everything, but it never even solves a single instance, so it never gets any feedback. The search space is too big. So we built in the syntax by positions of brackets, and then it makes progress. So when we run that on Blocks World, we run it for a while, and it produces, on several occasions, a program that solves arbitrary Blocks World instances. This is one such program. I'll go through it briefly just so you see what it is. The highest bidding agent here has this rule, 35, he bids 35.8. If this matches, he bids 35.8. Since he's the highest bidding, if he bids, he wins. So let's look at him first. We'll work from the back up. He matches when x4 is some string of blocks followed by one block. So the first stack has got to match x4, y naught. So x4, therefore, is all the blocks except for the top one. And that's got to match the one stack for this, because this binds. So for that to match, this thing has to be correct up to the last block. And the last block there has to be over here on stack 2. And then x7 can match as empty, and x1 can match as empty. So this matches exactly when the thing is almost solved, except the next block it needs to solve is right there. And then he grabs from 2 and drops on 1 and says done, so the instance is over. He knows how to solve that instance. He bids 35.8, which is pretty high. So if he doesn't match, then the next highest bidding guy is this guy. This guy bids 8.07 and will win the auction if he matches. This guy bids if this rule is satisfied or this rule is satisfied. If this rule is satisfied, then again, stack 1 is accurate as far as it goes, but there can be other stuff on top of it. And in particular, the next block needed, whatever the next one that's going to advance this, is sitting on top of stack 2. And as long as that's true, that the next block needed is on top of stack 2, and stack 1 is up as good as it goes, then this guy's going to match, because this can match anything, and this can match anything. So he grabs from 2 and drops on 1 and makes progress. All right, he's made progress. If this guy doesn't match, this guy might match. This guy matches when this guy is correct as far as it goes, and the next block needed is somewhere in stack 3. Whenever that's true, then this guy matches, and he grabs from 3 and drops on 2. So this guy will bid and win auctions and make progress, unstacking that, putting it on stack 2, boom, 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 until that gets to the top, then he'll put it over there, and then this guy will move it over there, and so he makes progress. If this guy doesn't bid, then this guy might bid if he matches. This guy matches just if stack 1 is correct as far as it goes, but there's other stuff, and who knows where the next block needed is. But if this guy doesn't match, then the next block needed is not on 3, and in these instances the next block needed is somewhere, so it's got to be on 2. This guy grabs from true and drops from 3, and he'll do that until he digs up under it. Then that next block needed is on top of stack 2, in which case this guy will move it over so they make progress. And finally, if none of these guys match, the only reason that happens is because stack 1 and stack 0 are wrong. There's something wrong in stack 1. There's some wrong blocks. In which case this guy matches because he always matches, and he unstacks from stack 1, stacking it on stack 3, and he'll just win auctions until he does that and remove them, and then these other guys can go on. So these guys solve arbitrary Blocks World instances. This is how it evolved. It took it almost 2 million instances before it learned anything, and then if you watch the screen line, you can see it started improving a little bit. It figured something out, and then right around here it figured it out, and boom, at this point it's solving infinite instances. The only reason that it didn't go up to infinity is because we have some algorithm in here that's slowly increasing the size of the instances we presented, and it's not catching on something. All right, we did 2 control experiments here. The first control experiment was to break property rights. And the hard thing about breaking property rights is breaking them in some fashion that might be sensible, because there's lots of ways to break property rights. The only say is it's broken. So the way where I broke them is to take advice from the classifier community. Various people were telling me there's a better way of doing bidding that you should really try because it'll experiment better, it'll learn faster, which is what's called zero-based classifiers in the classifier community. They were pushing this. And what they said to do was choose the winning bidder with probability proportional to his bid. Rather than choosing the high bid, choosing the probability proportional to the bid. So you do experimentation and try out different guys. Sounds like a sensible plan. The only problem with it is it breaks property rights. You're forcing guys to sell for lower amounts than somebody else is offering them. They don't like that. And so a guy who's almost done, he's going to take the world to some place where the next guy for sure is going to take it and solve a 100-block instance. Okay? he would like to sell it for 99 to that guy. But he can't sell it for 99, that guy might be willing to pay him 99. But he can't, he doesn't want to sell it, he doesn't want to pay 98 to get here, because when he sells it, some other guy who bids only 50 might win it probabilistically, and he wouldn't get paid the 99, he wouldn't make back his money. So he can't bid 98 to get there, he has to bid 40. And so you can't push money down the chain, and it totally breaks, it solves 4 block instances. The other thing we tried, since this program works so well, and it's such a compact program, maybe we put maybe we hand coded it all in, and certainly we have coded the program. You know, the fact that there's such a compact language is certainly contributing to our ability to solve this. So I figured maybe we could do it without the economy just by doing stochastic hill climbing search. So we gave it a program with 5 rules or something, and whatever we had there, 5 rules. I think we tried a few different things, and we just did hill climbing search where we kept on mutating a rule and seeing whether it improved it, and if it did, we kept that, and otherwise we went back. And we ran this for several hundred million post-production systems, whereas the other thing ran for a couple million. And it managed to get up to solving about 10 block instances, but that's as best as we could do. So it looks like the divide and conquer thing is actually doing something quite useful here. Okay, we also tried this on Rubik's Cube. Very similar, so I won't dwell on it. The encoding now is a 54 variable string, and the action string is over 12 actions that rotate any face of the Rubik's Cube, quarter turn. And the AI are variables that match one of the QBs, the color of one QB. You can try various rule creation procedures, for example, starting with all variable rules, gradually specialize by using mutations that remove a variable, setting equal to another variable with the color, same color as in the current cube. We try to number these things. They all work sort of similar. I'll tell you about something else in the S expressions. Result here, and then you have to have some way of presenting easier problems. There's sort of 2 ways of doing that. One is you start from the end, give it first problems that are 1 twist from solve, then problems that are 2 twists from solve, or alternatively, you can give it reward that's proportional. Start with a random cube and give it reward proportional to how many it gets right. If we started here with backing up from the end, it learned to solve about 7 rotations, using about 3 options for each rotation that it's got. So we'll be using like 21 options to solve this. So this is not solving Rubik's Cube, but it's actually, if I gave it to you, you'd think it was a random cube. It's solving about 35 million states that you can get to with these 7 rotations. It's factored that down into about 100 rules embodied in 200-300 agents. So it has factored in quite a bit, and then it's just not able to come up with agents that make progress after that. Here's what it looks like. Takes it a couple 100,000, maybe 300,000 instances till it's up here where it's solving sort of 7 block instances, and it just sort of levels out. And you can see the number of agents is here in green, number of live agents is fluctuating a bit. Number of rules is relatively constant. All right, that's post-productions. I want to go quick to get to web crawling. We also did S expressions. S expressions are parse trees, essentially, which have an instruction at each node of the tree. So we might have if here. If an instruction has arguments, then it's got 1 child for each of the arguments. So if takes 3 arguments, the first, then the other 2. So this tree says, and then down at the leaves, the tree ends when you get to a constant. So this tree says that if look 0, 0 is a color, that returns the color of the block on the bottom of the 0 stack is the same color as the color on the bottom of the 1 stack. And the color on the bottom of the 3 stack is empty, there's no blocks in the 3 stack. If those 2 are both true, then this guy's going to return 0, and otherwise he's going to return 0 minus 3. It's a subtraction. So we have S expression, that's an S expression. S expressions are what's commonly used in genetic programming. They're recently been used for evolutionary programming, perhaps. We have instruction set, false, various constants. We use typed S expressions to try and cut down the search space. So this equal is really an equal color. It demands that what comes below it is a color in both cases. We won't build trees that don't respect type. With types void, integer, boolean, and color. Okay. So an agent then consists of 2 sub-expressions. One is a void sub-expression that takes actions on the world. We implement that, simulate the actions. Then we calculate the integer one, which returns a bid. So it's going to sense the world after the action. If this guy's going to take some series of actions, then we'll sense what that does with our integer guy and return a bid. Oh yes. So let me say in the instruction set, there's grab from stack I, drop from stack I, look ij, which I mentioned, done, and we also in some of the runs, give it num-correct, which I mentioned before. That's a hand-coded feature that we saw it trying to evolve, so we handed it. I'll talk about runs both with and without it. Num-correct tells it the number of blocks that it has right on the 0 stack. Yeah.
So this can no longer ask the question, is there a red block in stack 2, is that right? Whereas the previous language could?
Yes, this is not, there are things that this thing can't do, which maybe, constrains it. It's not going to solve arbitrary blocks problems either. It gets up to sort of 200. This cannot, yes, this could. This actually could. We have if, then, else, and we have a for list here.
I see.
So this can ask if there's a block in stack 2. Yes. But I'm not convinced it's fully universal anyway. Here's how it does if we give it num-correct. It starts learning, and it, I guess here solve, red is the size of the thing it's solving. It gets up to about 180 blocks here after 1.6 million. And you can see the number of agents is increasing in green here. It gets up to about 2,000 agents. And if we modify the bit structures in ZCS, dango, nothing happens. Okay, how is this thing working? It's sort of interesting. I'm running out of time, but it's probably worth mentioning. This guy built these crazy S expressions that are, that if you look at them, they go on for a few lines of code and you never understand them. But if you run up through Maple and then look at them, you can figure out roughly what they're saying. Basically what they're saying is every one of them has a bid which is A times num-correct plus B, where A and B are almost constants. They're expressed, but they're basically constants. And the agents come in 3 types. There's a cleaner, A and B differ from the agents, and the actions differ from the agents. Some of them I call cleaners. Most of them are stackers, like almost 2,000, and then there's a few closers. The way it works is the following. This is what it involves. At the beginning of each instance, one of the blocks at the bottom here is, probably the bottom one is not the right color. Almost certainly the bottom one is not the right color, but if the bottom one is, the next one isn't because they're random. So num-correct is basically 0. And so nobody wants to bid very much. And who wins the auction? The guy with the biggest constant B. And what's his action? His action is to clean from stack 1. That's what he does. Clean means to take several blocks off stack 1 and put them on stack 2 or stack 2. He takes the blocks off. He wins the auction. Now we hold another auction. Still, these guys are wrong. Nobody really wants to bid very much. He cleans some more. So we start out with 50 blocks in stack 1. After 25 auctions, he's cleaned them all off. Okay, now it's clean. Now, all these different stackers, what they're doing is they're trying different ways of pulling out some of these blocks and putting them here. And because there are 2,000 of them and they're trying different ways, one of them gets something right and makes some progress. And since he's looking ahead to try that, he's looking at a series of actions, remember. He knows what he's doing. He's looking at a series of actions that take something out and put it here. But because he's looking along a series of actions, he looks far enough ahead that num-correct shows him that something's made progress. And he bids more than everybody else because he's bidding with a big num-correct. So he wins the auction, we make some progress. Then another guy does the same thing, then another guy does the same thing. That goes on for 200 auctions. And then the last guy wins the bid because nobody else can improve num-correct. He's got the same num-correct as everybody else. And he has a higher constant B, and he says done. And they've solved it. So they evolved this collection of 2,000 agents that collaborate in this way to solve. And they're all paying, each guy's making profit, right? He's getting closer, he's getting paid more than the last guy. If you don't have num-correct, you can in principle write it like this. But that's too long for it to evolve. It evolves an approximation to it and does essentially the same strategy and starts making progress, getting up to about 50 block instances. You'd think you could maybe evolve num-correct, but once it's sort of gotten into the other strategy using an approximation, it evolves all its constants and it's pretty happy. And even if num-correct evolves, it's not clear it's going to be stable. However, we managed to get num-correct to evolve by adding a node to the population, the instruction set to the population, Rij, which just returns I with probability 1/2 and j with probability 1/2. Just randomizes the situation. And that seems to interpolate between the expressions and smooth the fitness landscape. When we did that, it actually evolved the exact expression of num-correct. And it started going up like crazy, but it only got up to about 20 blocks after several weeks. Because it's taking so long with this crazy thing it's computed that's actually computing num-correct, but it's got all this other junk in it, that it's about 100 times slower than the num-correct that we implement when we implement num-correct, and we run out of computer time. But it looks as if it's just 100 times slower, and if we gave it 5 years of computer time, it would solve arbitrary, get up to 200 block instances. Okay, we did essentially the same thing in Rubik's Cube. Learned to solve the lower half of the cube, basically. We did the same thing for rush hour. Rush Hour is a commercial game where you're trying to move cars and trucks out of the way. It's puzzles, a set of puzzles. It learned to solve 9 of the 40 problems simultaneously, which is arguably pretty good. Gary Flake and I, by the way, proved that the n-by-n version of this is p-space complete. Sort of an interesting construction. But anyway, so, you know, agent 1, one guy takes it there, 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 and out you go. It learns to make progress. All right, let me talk about focused crawling, which is the latest application. What's focused crawling? I guess you people know, but what I'd like to have is I'd like to have a program where I give it one or more pages, possibly with some indication of the information I really want, and it should return all the similar pages on the web, or maybe even better, the information I want from those pages if I was really smart. And the method that I want to get there is using a focused crawl. So there's some page that I'm going to pay reward for here, and some page that I'm going to pay reward for there, and I'd like to be able to set out from here and know that this page is an ancestor of pages that I want, and then this page is an ancestor, and this page is an ancestor, and go there without going down all the various other links that I might go. So I have essentially a smooth crawl. I might go down, I might add an occasional link that I don't want to my tree, but basically, you know, there's a mistake. I'd like to get there pretty smoothly. To do that, I've got to learn to recognize what the parents of good pages are and what their grandparents are. So if the pages I want are, say, neural net papers, those might live on the pages of computer science researchers, and I might get to those from computer science departments. But any keywords that I use to look for computer science departments might be very different from keywords that I use to look for neural net papers. So I've got a real problem of assigning credit, understanding that, you know, what kind of features that I want to look for here. I've got to back credit up. It's another problem where I'm trying to back credit up a long sequence of things, and that's why it seemed like this might be the right problem, a good problem to try. For the stuff I'm talking about, I'm not giving it pages really, I'm giving it a set of keywords. So any page on the web that has all 10 keywords that I give it, I give it a reward for, and it's supposed to find those pages. So therefore I can implement a program that tells me when I get a reward and I can run my algorithm. Otherwise you've got to adjust that problem. Okay, so what do agents do? Agents here are going to, so when we're doing this, we've got, when we're running this thing, at any given time, we've got some set of pages that I'll call traverse pages that we've already added to our search. There's a frontier of pages that are pointed to by links from that search, from the traverse pages. And I'm considering which one of the pages in the frontier to add to my search. My agents are going to bid on those pages in the frontier. And an agent is going to bid on a page in the frontier if and only if it contains a set of keywords that's identified with that agent. That's what an agent is. It's a set of keywords, and if it sees that a set of keywords and a bid, and if it sees that agent, if it sees a page in the frontier that matches its set of keywords, then it bids. I'm going to add the winning page, which in some sense is I'm building the best to my traverse set. I'm getting new agents by mutation of existing wealthy agents. Initially, I'm getting agents by taking a page that's on my frontier, and anytime nobody matches, I take a page that's on my frontier at random, and I add some keywords, take some keywords from that, and build a new agent with it. That's how I get initial agents. And then I'm getting new agents by mutation of existing wealthy agents, taking a page that they match, and choosing keywords from that page to add or mutate them with, using a variety of statistics to decide which keywords are the best. We use TIF, differential document count, information gain. If you look in the paper, by the way, don't look in the paper for at least another week, because there'll be a better version there a week from now. Basically, we didn't invent any of these things. We just took them out of the literature. And so hopefully we get a situation where there's a goal page which has value 10, and some guy bids 9 here and 8 there, and we walk down to where we want to get to. We use 2 models for assigning bids to the agents. One thing was with standard bid epsilon agents like we had before, where an agent has a fixed bid. When a new agent comes in, we set its bid to be epsilon higher than the next guy bidding the first time that's applicable. That worked okay, as you'll see. Even slightly better was to use agents that actually estimate their bid here, because page fetches are a little expensive. So the bid the guy makes is the average he's gotten paid over all the auctions that it's recently participated in. And we use a second bid auction, where whoever bids the amount you pay is actually the second amount in the auction. Because then from economic theory, then it pays you to bid as much as you possibly can, as you can afford. Whatever the true value is, it pays you to bid. So this guy is being forced to bid his true value, not to make any profit. Because when you win the auction, you win because the second bid is lower than whatever you bid, and then you make a profit. And anytime you're going to win it, you sort of expect to want to do that. So we use the second bid auction here. And that seemed to make, I had used these bid estimating agent kind of things before, and it never really worked. I think the combination with the second bid auction was the key here. Okay, so here's the results. We're comparing Bayesian models. This is sort of a straw man benchmark that people use, which looks at keywords and computes, it attributes a probability to a page being a goal page by whether it has some keywords in it that are chosen from statistical analysis of the web. You can either use binomial, whether the words are in the page, or multinomial, which works a lot better, the number of times that the words are in the page.
If you wanted neural network articles,
Yes.
then you would give it keywords from a neural network article.
Yes, that's right. Yeah.
So you would seed it with that.
Yes, that's what I would get.
Right, so for this naive Bayes models, there's no chaining in the training.
There was no chaining in our training. This is a pretty naive model. So I probably would like to have a better comparison actually. But anyway, we beat the naive. We're not the first people to use this naive model, so I don't feel too bad. The Bayesian binomial really doesn't do very well. You can see tracks that it's running where it reached maybe 30, maybe 20 here. It found 20 goal pages after doing 20,000 web pages. The multinomial model does a little bit better at getting up here to finding 80 pages. When we run the bid epsilon Hayek, you've got all these red runs. You can see it's getting up sometimes. Sometimes it gets stuck, but sometimes it's getting up to find all the goal pages we know about up here after, getting up reasonably well after 20,000, 30,000. And the bid estimating Hayek is finding sort of, some runs it's finding all 150 of them after sort of, I don't know, 10,000 page fetches, which is pretty direct. And I don't have the slide, sorry I didn't manage to include it, but if you take, the application that I see for this model is, you train this thing in background on your home computer, there's some subject you're interested in beach volleyball pages, that's what this is. And then it develops a trained model, and then it's quite efficient. I mean, this is including the learning. If you take this guy now and you run it from a random starting page, it finds all 150 of these guys in a flash, in sort of 500. It knows what it's doing at this point. So you run this in background. Now, first of all, only 15% of the pages on the web are indexed, so you might find a lot of pages you never would have seen that you're interested in. And then as new pages are added or not, it alerts you. So it's actually conceivable to me that this system, as it stands, is a sellable software product. Although
Well, it doesn't do the classification, right?
no, I'm assuming you give it. I'm telling it. In order to train it, I have to have something that tells it when it's found a goal page, and I'm giving it a collection of keywords. Whenever it finds a page which has the following 10 words that pertain to beach volleyball, that's a page I want, and any other page I'm not paying for.
So did you evaluate this in the training test paradigm? In other words, can it find pages that you didn't train on?
Oh yeah. We trained it on what do you mean trained it on? That we didn't reinforce it for.
That you didn't reinforce it.
I mean, we started off with 15, and then it finds, in some sense, it finds every time it gets to a page, we find it. So I don't know I'm not sure what that would mean.
Okay.
When I run it again, it finds them again. I mean, I'm not rewarding it then.
Yeah, okay. I guess the question is, once the thing is fully trained, so it finds all 150 pages quickly, or the next 150 pages it finds, or the other ones that it finds among the first 150 also relevant.
It doesn't find irrelevant pages. Well, and it's supposed to find pages that are antecedents of relevant pages. So
But it doesn't say done on this.
It doesn't say done on anything. This guy isn't saying done. He's just running it. So I'm not sure how I do that. Now, I mentioned that the economy that I told you about, and everything through here is a single commodity economy. Everybody, guys buying the world. But actually, for this problem, there's a much more natural multi-commodity economy that we really would love to see implemented. Which is, agents buy a page, and they own that page, and they get paid when another agent buys a link from it and buys the page there. So then you have multiple agents owning different things, and an agent that buys a page that leads to two different guys can get paid twice. That's a more valuable page in some sense. At any given time, you're adding the best page, maybe the highest bidding page, but the flow of money is very different. It's flowing to guys who own this commodity or that commodity, multiple commodities in the system. So it's natural to try this, but we don't have the software at the moment. All right, so that's the talk. I claim that my economy seems empirically to achieve credit assignment and produce this modular structure. It certainly gets deep chains and stable cooperation among these guys. For harder problems, it's not clear how you can continue progress. When you solve half the Rubik's Cube, how do you find another agent that makes any progress without destroying what you've got there? We weren't able to do it. A mutation of a current agent doesn't do it, and we're out of luck. There's still a big search there. I tried early on meta learning to do this. So instead of just doing random mutations, we had other agents that mutated guys. They were capitalists that invested in the system, and they owned the guys that they put in there. And we pumped money back to the second level and tried to meta learn how to create these guys. And these guys actually learned how to create agents better than the existing random mutations in the sense that we got to better results with fewer agent creations. However, the overhead of doing this was slow, and it took longer. It wasn't getting us better results overall. So we dropped it. It certainly wasn't a very big win. I suspect that that's true because it takes us 2 million instances to push enough stuff into blocks world so that it understands blocks world. Pushing it up to the meta level is it's getting filtered. It's not getting nearly as much reward. So if we had computers that were 3 orders of magnitude faster, maybe we'd solve that problem. It's maybe only a constant factor, right? Evolution has a factor of 10 to the 20th. Maybe it solves that problem. It's maybe just a constant factor. And in this model, though, in this economic model, it's natural. I'm not talking about it here, but it's fairly natural to do that. You can pump money back to these. They're investor agents. They invest in this new guy. They give him this startup capital, and you pump money back to them. And the investor agents, the creation agents that are good will survive, and it's easy to evolve them and do credit assignment on them. The problem is getting them enough training so that they learn something. I think we've demonstrated that there is at least the possibility that this thing extends to practical applications. And finally, plug my book again, look for it. It should be out next fall. If you like this talk, it's a big picture of how evolutionary computing has extracted an understanding of the world and how mind and consciousness and everything you want to know about it arises from there. That's it.
Well, thanks for a very interesting talk. We've got good time for questions.
So, first of all, I don't understand what it means to solve half a Rubik's Cube.
What it means is you got half the cubies right.
They are right. Okay. That's not clear that that's half the cubics.
When I'm solving Rubik's Cube, you give me Rubik's Cube. I start solving it from the bottom, and I get the bottom half of the cubies right. And then at that point, I can't figure out how to make progress either. If I want to make progress, I've done it once. It took me 2 days. I had to take notes to get the top thing right. Okay? Yeah. After 2 days of thinking about it, I got the top thing right. That's where this thing gets to that point. If you give it reward for how far it's gotten from the bottom, it'll get up till it gets to the exact point where I'm stuck. And then it can't figure out the next agent.
So you're counting continuous cubies or something? Like contiguous cubies?
Yeah, so I think we tried to. I think it can do about as well with spattering, but you can certainly trained it to get the bottom and the middle right. I think it gets, maybe it's missing one in the middle. I can't remember where it gets stuck.
So what is the reference to Hayek that you had there?
Hayek is what I call the program.
No, I know, but I mean,
why do I call it Hayek?
To do with Friedrich Hayek.
Yeah, absolutely.
Yeah.
Friedrich Hayek was all about exactly these kind of mechanisms for pushing incentive through economies. And so I thought it was an appropriate name for this program. He also, by the way, did psychology, so he was interested in mind problems. But in particular, he's sort of the inspiration, I think, ultimately going back for these notions that conservation of money and that the economy is basically doing dynamic programming. It filters from Hayek. I'm not the first person to mention that. If you go to Miller and Drexler knew about, they didn't apply it to evolutionary computing and things, but they had ideas like this. They applied it to comparing the economy to the ecosystem.
The main thing about Hayek is I think that he says planned economy is impossible because that would mean solving a system with, I don't know, million unknowns, and you just can't do it.
But he also,
But you here,
Yeah.
before, you were talking about how if you don't put certain constraints on, how the various agents are going to do, well, are just going to suck money out of the system and sort of not invest them. I mean, they will do essentially what Enron did, and they will do essentially what they do in Eastern Europe these days.
the constraints you need on the economy are conservation of money and property rights. You have to, so in my system I impose
So why
those because I'm
doesn't
ready
it
to
work
go.
why doesn't it work in a real economy?
It does work in a real economy. The economy functions to the extent that you enforce conservation of money and property rights, which it's almost entirely enforced in the real economy. Right? You get a certain, so to the extent that you have, to the extent that you have fraud that's violating property rights, arguably, you can take two pictures on that. Anyway, it cleans out, right? Enron is gone, right? There are fluctuations. I'm not saying it's a smooth economy. Actually, in a previous, I have a slide somewhere, I don't have it with me, showing in an earlier version of this, which didn't work well, I can't remember the context, showing an amazing business cycle. But you know, when the system can get fooled temporarily, but eventually it's doing dynamic programming, it's pumping money through, and it's learning what to do.
Right. Well, you've got long-term actors, right? It's sort of a big deal. So
I've got
you're not dealing with some fly-by-night operator. You're going to establish, you try them out for 10,000 times, and if they're not doing well, then you drop them and go to some other business. Transactions don't happen. Yeah, they're doing.
No, that's not true. I mean, guys come in, new guys can come in, and they enter the system, and they're maybe doing something stupid, and they survive for some random reason, or because they fool somebody for a while, and then they get it removed. I don't try guys out for 10,000 instances before they come in here. New agents.
No, that's not what I mean.
Yeah.
What I mean is that there are companies in the real economy that survive well because people only do business with them once, right? And I mean, you don't have a reputational mechanism either. What you have is, well, I did business with them, I got burned, so I'm not doing business with them again. I did business with them 30 times, they're a financial advising firm, and I discovered that, their advice was good 16 times out of 30 and bad 14 times out of 30, or they win or not, I don't know. I've got to keep going for a while.
My guys don't know anything about it, right? If my guy does business with the guy once, even if he gets burned, he'll do business with him again.
Yes.
Until he goes broke, right? One of the other goes broke. That's going to continue. Assuming that we're getting the same state where they both act.
Well, okay.
In the real world, that won't happen. People are smart, and people make valuation decisions that arguably make things work better. I think. This is from years ago. When I first started doing this, we had problems getting the valuation. I mean, there's a problem with new agents coming in because new agents can pump money into the system. That's how we got the business cycle. You get these speculative bubbles. I mean, it's really amazing where the system. This was an old. We've gotten rid of this problem in various ways, which I'm not sure I fully understand. But we used to get this occasionally this amazing business cycle where guys would be bidding more than the final payoff of the systems. There's no way that the ultimate guy's going to ever make payoff. Why are they doing this? Because this was back when we had capitalist agents in the system that were bringing in these venture capital firms. I'm not joking here. This was before the bubble too. This was 5 years ago at least. They're coming in. The new agent's coming in. He's being created with money by a venture capitalist. And he buys at the top and pays the previous guy. So this guy's happy to do it because somebody else is going to pay even more. The next guy is their bid excellent agents. They keep on coming in and they pump it up, and then it's not stable. It lasted for a while, amazingly enough. Then it would collapse. Then it would come back again.
So the venture capitalists over time are supposed to get smarter, but it might take a while.
Yeah, right. Yeah, that's right. There's a big layout. Right. And as I said, I was never able to get the venture capitalists nearly as smart as I wanted when I dropped them from the system. But the venture capitalists were inducing this incredible boom, at one point, this incredible boom and bust model of bubbles. I should drag that slide out and publish it. I'm not sure it's published anywhere, especially in retrospect of what's happened.
I have more questions, but
yeah. This is about the way you are getting new agents into the system. Like you say you are doing mutations. Are you doing something which is like similar to the crossover thing in JNet algorithms? Like,
Yeah, so you can do mutations which are crossovers of two agents. I won't swear that that's not in this code, because Igor wrote most of it, and I don't know anyway, but we've tried with and without, I don't think it makes a whole lot of difference. Whether mutations are sort of point mutations or crossover doesn't seem to hurt much. I'm not 100% sure. I don't think it's in the web crawling, actually, but it might. I'm pretty sure it's not in the web crawling. The web crawling is much more hands-on mutations where we're doing TIFF-diff and stuff to try and suggest good keywords. But it might be in some of the Rubik's Cube results or some of the box results. Or it might not. It didn't make much difference.
I'm sorry, maybe this was explained by your models, but when you're doing the web crawling, are you learning the set of keywords that's most discriminative, as a byproduct of the process, are you learning the set of keywords that's most discriminative of the kind of information need that you're trying to satisfy, or are all the keywords weighted?
We're learning, no, we don't have that. So, yes, and we have a set of, I mean, one reason why this is effective, maybe more effective than other approaches, if it is because it's got a lot of different stuff. You know, you usually have one set of keywords that you're looking at. I've got hundreds of agents, maybe thousands of agents, and each agent is looking for some set of pages that it thinks are good, and it has some set of keywords. So there's no one set of keywords. I don't know how I compile this thing.
Sort of the intuition being that as you search the web and find more pages about what you want, your model of
My model should be capturing, yeah.
should be shifting.
And it is shifting, and it's, you know, there are different agents in there bidding different amounts, so they're in some sense predicting that you're further from or closer to the goal page, but also munged into that, and it's not really so separable, is they're predicting the probability that somebody's actually going to buy from them, so that a guy with more possible ways to get to a goal page might also get more. The interpretation of their bids and their keywords is not so straightforward. We haven't looked at it by hand very much.
Well, I have several questions about how you might change the system to get better behavior of one kind or another. Let me throw it to you, and you can answer whichever one you think is more fruitful. One is, you're doing chaining, which is like Plan XD. You could go context free and have subroutines. So, you know, I might pay this agent to do something for me, and then that agent to do something for me. One reason that might be useful is the first agent maybe is going to be some information gatherer. You know, the first agent is going to act on some hypothetical version of the world. In the case where you don't have a for loop, it might explore and try to find see whether there's a red block toward the top of pile 1, and it might do that by paying off other agents and so forth.
So I'll address that, and then you can come to the question 2, Fred. So one can imagine much more complicated information economies, and it would be cool to evolve them. But I'm not quite sure of the model of how to do that. For example, where you've got an agent that's a subcontractor that's going to find out some information and give me that information. So there's a chicken and egg problem here. An agent can't write on some memory a word until I know how to interpret that word. And I don't know how to interpret that word until he writes on it. So I don't know how to bootstrap and get more complicated stuff like this and get it to work. I've tried various models. And I've never succeeded. I'd love to have a way of evolving, you know, more complicated information processing, subcontracting of, defined statements. We've tried various ways of putting defined statements in and having them compensated. I don't know how to do it. A defined statement is something that defines an instruction that then is used in other agents.
Right. The other thing that I was wondering about is the role of randomness in the bidding process, for example. So what you have now is sort of like a decision list ultimately, although it's a little more complicated because but you know, whoever's at the top wins, and if they fall through because their conditions aren't met, or possibly because their bid is too low, because I guess the bid can depend on the conditions, then it goes on to the next agent and so forth. But you wonder whether there shouldn't be a little bit of jitter added, so that sometimes lower bids can also win. And I can imagine a number of reasons that might be good. One is empirical, and that you did a better job on one of your experiments when you threw some randomness into the decision-making process inside the agent. So you could institutionalize that. Yeah, I'm sorry.
The web crawling actually has something like that in it. The web crawling new agents that bid close are winning. I was a little against that because early on in some of our runs, stability of order was actually more important, and having it randomized was worse than having one, when two guys essentially tied, having one guy always win. And so what we would do actually is add a small amount to his bid if two guys were tied. And just leave it up. But it seems
But
to
in
be
principle, the
working.
agent should learn that, it's important for them to win all the time, they should just bid more. Or if it's important for
If they
them to
can.
go after some other guy, they should just bid less.
Yeah.
Plus to.
Right.
to-
It could be that adding a little bit of jitter. So like I say, in the web crawling thing as it is implemented, it is allowing a novice agent, the guy who's just entering somehow, or pretty new to outbid a previous guy paying a little bit less, 82%.
Well, one reason that you might expect to, I have some intuition, I haven't totally worked this out.
Once, I think it's allowed. I think it's allowed now to jump ahead once in the current system. I'm not sure how you know. Yes, I'm not sure how.
So that's a rule which is trying to make sure that everybody gets to compete, right?
Yes, that's right.
Right.
Yeah, I was skeptical, but anyway, it's in there, I'd say if you were.
Yeah, I mean, the bid is part of it, but then there's sort of a notion that if you give somebody a start, then you might be able to accumulate more money, eventually do better. So you can't bid that well now.
Right, exactly.
But it needs to build up some capital
Yeah,
by
right.
virtue of doing better.
Yeah, it makes some sense in the bid estimating agent, who's, if he starts estimating that he's really worth more than he thought, then he'll bid more.
Yeah.
For fixed bid agents, it doesn't make so much sense, which is what some of these agents were returning functions of what they're bidding with num correcting them, and some of them were fixed bid agents. We've used various models.
So let's take one more question if there is one, and then let people go, and anyone else can stay after and talk to the speaker. Okay, well, let's thank the speaker again.